Hello. Today we're going to talk about topic 4, section 6, probability calculations. So, in the study of probability, we use a theoretical world to predict the practical world, all right? Because that's what stat is trying to make predictions, okay? So, just some backstory. Some French mathematicians were one of the first to develop mathematical models of theoretical probability by looking at games of chance. All right, they were trying to increase their money, right, when they're gambling. Then the two Scottish churchmen were the first to come up with insurance, and that idea was set up to pay for widows. Okay, in case the churchmen were to pass away, the widows could still live comfortably. Okay, so just some interesting backstory of probability. Now, here's the probability scale. We talked about this before. So when we talk about probability, we use fractions or decimals. All right, we talked about impossible, never going to happen, 100% going to happen, 50-50. It is also acceptable to give it as a percentage. Okay, just make sure that you're doing the conversion correctly. All right, too many times I've seen people write 7% as 0.7. That is not the same thing. Okay, so make sure you're not mixing up your conversions. Okay, 7% is equal to 0.07. Okay, all right. The modeling events that you're probably used to by now should be Venn diagrams and tree diagrams. Some issues that I've seen students have with Venn diagrams is not adding all the parts. So if I want to know the probability of getting something in red, okay, I would have to add the 7, 5, 3, and 15. All of those make up 30, all the probability of the entire red circle. Now, for the probability of the yellow circle, you would look at 4, 5, 3, and 17. All of those correspond to the yellow circle. So just knowing how to read a Venn diagram is very important. Okay? Oops, sorry, went too far back. All right, so tree diagrams, that's when you have multiple events. Okay, so multiple outcomes. So like flipping a coin or flipping two coins. So the first option is you can either get a head or tail. And then the second option is a head or tail off of that. So then you kind of get a tree formation, okay, with branches. It's important that you understand what I mean when I say probability of A and B happening and the probability of A or B happening. When I say I want to do dinner and a movie, I want to do both things and only both things, okay? I would be very disappointed if I said I want to do dinner and a movie and I only got a dinner, right? I'm high maintenance. It's just how I am. All right. However, if I said dinner or a movie, that leads me to be a little bit more flexible, okay? That I want to do dinner, we could do a movie, or we could do both, okay? So or is everything. Everything of A, everything of B. Okay? Now, mutually exclusive, okay? You've got to know these terms. It's very important. It's going to be thrown at you all the time in statistics. Mutually exclusive means the events do not overlap. They can never happen at the same time. Rolling a 6 and getting a coin flip of tails, they don't have anything to do with each other. I can't do one thing and have both outcomes. Okay? I can roll a dice and get an even or a 2. Okay, that can happen. Those are not mutually exclusive. They can happen at the same time. Okay, however, mutually exclusive can't happen at the same time. So like rolling a prime number and rolling a 4, those are mutually exclusive. It's never going to happen at the same time. We're going to start with our first example. So we have all the whole numbers the positive whole numbers, so 1 to 25, and we're going to draw one at random. What's the probability that the token is divisible by a 3 or by a 4? So what's the probability that it's going to be divisible by 3? Well, hopefully you know that the set of all those numbers, let's see, I guess we'll write it this way, is 3. Ooh. 3, I'm going to write this all out. 6, 9, 12, 15. That's a rough looking 15. All right, 18, 21, and 24. The probability of a 4 rolling is the set of numbers 4, 8, 12, 16, 20, and 24. Ooh, I did not do my little brace there. Whatever. All right, and then the probability, well, hold on. If I just added those, okay, look at how many options there are. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6. That would 8 plus 6 over 25 numbers. That's a lot of options. 14 numbers. Okay, but think about what you just did here. Okay, if we listed all the numbers, we have, let's see, 12 is happening twice, and 24 is happening twice. Those numbers are being double counted. So when you do an or statement, okay, well, maybe I should do this in red so it stands out. Hold on. When you do an or statement, you want to subtract the overlap. So what's the probability of a 3 and a 4? So divisible by both 3 and 4. Well, that would be 12 and 24 option. So we'd have to do minus 2. And now our probability is 8 plus 6, which is 14, minus 2, which is 12, over 25. Okay, that's the probability. Yes, you can write that as, 0.48 or 48%. Okay, any of those would work. Okay, so let's do the next one. Students were surveyed whether they eaten apples, bananas, or both in the last month. So they found this. So find the probability. Let's start with A union of B. So what that one is saying is let's find the probability of A or B. Okay, that's what we did up here. So that's the probability of the first one plus the probability of the second one minus the overlap. And how do we write the overlap? This and statement, we write it this way. This is the same thing as probability of A and B. So we subtract the overlap. So we would do 0.6 plus 0.2 minus 0.1, and that first probability would then be, what is that, 0.8, 0.7. The next one, the probability of not A, well, the probability of A happening is 0.6, so the probability of not A is just 1 minus the probability of A. So 1 minus 0.6 is 0.4. All right, now the next one, the probability of not A and the probability of B. So for this third question, I would probably draw a Venn diagram. That would just make things a whole lot easier. And you could have done this in the beginning, all right, but now it's going to be super helpful. So we already know that there are going to be two circles because probability of A, probability of B, two different events. However, we need to know that A and B means that the circles overlap. All right, so the overlap has to be 0.1. And all of A is 0.6, so that makes this part, not the intersection, be 0.5. And then this part of B would also be 0.1 because together they make 0.2. All right, so, and then we can tell that everything outside is 0.3. So not A or B, okay? because if I add them up, 0.5, 0.1, 0.1, I get 0.7, right? And the whole rectangle has to add up to 1. Okay, so now let's see. We want to find, how am I going to do this? We'll do this high. No, we can't do green. Okay, so not A. So not A is everything outside of A. Okay, but we also, it says and B. Well, B is, I guess I should do that a different color. All right, and B is this part. So what we want is not A and B. And is the overlap, okay? And is overlap, okay? So the overlap here would be 0.1. Okay, so for that third question, that third probability would be 0.1. Now the third example has to do with a deck of cards. You should be comfortable with knowing what a deck of cards is. If you don't, study up. If you have any questions, ask me in class. I understand we all don't have the same background. Okay? All right, so here they describe what a deck of cards is. So now we want to find the probability that the card drawn is a red card or a card that has a face on it. So we do the probability that it is red plus the probability that it is a face card minus the probability of both. So how many red cards do I have? 26 out of 52. How many face cards do I have? That's all these jacks, queens, and kings over here. So I have 12 face cards. And I have an overlap of 6 red face cards. So 26 plus 12 minus 6 is going to be 32 out of 52. And we can simplify that to 8 out of 13. There we go. So that's the first question. The second question, we want to do a red card or a card with an A on it, so an ace. So probability of a red plus the probability of an ace minus the probability of both. So we have 26 red cards, 4 aces, and 2 overlaps. Or 2 overlaps. This is how you show your work, guys. Okay, so 30, then minus 2, so 28 out of 52, which simplifies to 7 out of 13. There you have it. All right, so let's do more examples from the section questions. I don't know how, that part of Cognity, whatever. So example 1. Here we want to find this probability, so I like to highlight. Okay, so we want the probability of A and M. So let's do the probability of A. Well, that's the entire red circle, which, why am I doing it in green? Here we go, we can just do it this way. It's already red. And then not M. We'll do that one in green. So that's everything outside of M. Well, outside of M is everything outside of the blue circle. So we are looking for the and, which means the overlap. So the overlap would be 15. That's the answer for number 1. Okay, now for part 2, or for example 2, we've got this set up for paper version, online version, or neither, okay, for a newspaper survey. So I'm going to go ahead and draw my rectangle. So you can tell that it has both or neither. So that means the circles are going to overlap because of the word both. So we have paper and online is E. Don't know why, it just is. Okay, so we know that 380 people said neither. So 380 people are out here. All right, we know that there are 350 online, so this whole number has to be 350, and 125, so this whole circle has to be 125. But we don't know how many read both versions. Okay, so let's think about this. We know that the probability of, was it paper or online is just the probability of paper plus the probability of online minus both. Okay, so probability of paper or online is just hold on, highlighter, it helps. Okay, so the probability of this is all of this section. Okay, so that has to be 420, because if 380 people are on the outside, this part has to be 420. Okay, or I got it from doing 800 minus 380. 800 is everybody in this rectangle, and 380 is everybody outside. Oh, I hope I'm making sense. Okay, now I'm sorry, this is probability. We should be doing fractions. These are not exact numbers. So this is out of 800. So we know this is 420 out of 800. Now the right-hand side, probability of paper is 125 people over 800. Probability of online is 350 out of 800. And the probability of both, well, we don't know that. That's X. So I add these, I get 475 over 800 minus X over 800. They all have the same denominator, so just go ahead and cancel them out. 420 equals 475 minus X. So X has to be, what is that, 65? No, what am I saying? 55. Okay. All right, so a picture helps. Okay, I like to use colors and highlighters and kind of overlap things. There are such thing as erasable highlighters. I highly encourage that. Highly, yeah. Anyway, sorry. Long day. Get the erasable highlighters. Okay, it helps in case you make a mistake or you're just going to have to keep redrawing the Venn diagrams. Whatever. Okay, but colors help. Now for example 3. A group of 60 people are going to an amusement park, and now we've recorded who like roller coasters, who do not like water rides, and who don't like either kind. Okay, so they want us to determine which Venn diagram. We're not going to do that. We're going to create our own. Okay, so we know that there are 60 people going on a trip. So there are 60 total people. I like to put the total up here. It just helps me keep track. All right, now the number of people who like roller coasters is 42. So we know this circle has to be 42. Now the number who do not like water rides is 23. So the people outside of water rides is 23. Okay, so that would be, here, think of it like this. Okay, so we'll do it. Those who like roller coasters is 42, so that represents A and B. So A, well here, we're going to have several. A plus B must be 42. We also know that those who don't like water to rise is 23. So outside of water is A and D. So A plus D is 23. And the number who don't like either kind of ride is 8. So those that don't like either kind out here is 8. So D is 8. Okay, so now we've already figured out 1. So now we can go ahead and plug it in. A plus 8 equals 23. So A must be 15. And we can keep going, right? A plus B is 42, right? We have that as a formula. We can also see it based on the graph. So 42 minus 15 is 27. Okay, so again, I did A, A is 15. I meant 15 plus B equals 42. So that's how we got B. And then we've got all the values. We know A plus B plus C plus D must add up to the total of 60. And we've already got A, B, and D. So now we just solve for C, and we get 10. Okay, so it helps to try and find your own answer first before you look at all the multiple choice options. Okay? So now for union probability, which we've been doing this whole time, A or B. Probability of A or B is the probability of A plus probability of B. Hold up. Minus the overlap. Uh-oh. We gotta get that on there. Okay. All right, so you want to correct that on your notes. Okay, so that was a typo there. Now, so here, if we draw a card out of a standard deck of cards, find the probability that it's a face card or a spade. So the probability that it's a face card or a spade. Probability that it's a face card plus the probability that it's a spade minus the probability of both. So the probability that it's a face card is, let's see, how many are there? Jack, Queen, King for 4 suits. That's 12 out of 52. Spade, there's 13 of those. And there are 3 face cards that are spades. So we should get 22 out of 52. And yep, that simplifies down to 11 over 26. There you have it. Now for conditional probability. That occurs when we have some knowledge about the outcome. Okay, so it's shrinking our sample space and therefore increasing the probability of an event occurring. Okay, so that's, what's the probability that I mowed my lawn given it's a sunny day? Much higher probability than the probability of me mowing my lawn given that it's a rainy day, right? So that given condition changes your probability. Okay, that's what conditional probability. So how they write it is with this bar in between it. And that's the probability that A happens given B has already occurred. So you do the probability of both divided by the probability of the given. Okay, I see people mess up all the time. They do the probability of A. It's always divided by the given. So let's do an example. So take a second and read this. Now, we want to find the probability that one has done business in Mozambique, given that they have not done business in Angola. So, the probability that they have done business, given they have not done business in Angola. Okay, so not Angola. So we do the probability of them both happening. oh, no, and both. A and not A, divided by the given, so the probability of not A. So let's start with the first one, the numerator. So this part is the probability of M happening. So that's this blue. And not A, so everything outside of A. All right, where they overlap is 18. So that number is 18 out of 60 total. Now for the denominator is going to convert to, ooh, I did not write that nice. Didn't finish my parentheses there. So let's go back. So probability of not A, so everything outside of A, that's going to be this 18 here and this 24 there. So 18 plus 24 is 42. So this will be 42 out of 60. Well, a fraction divided by a fraction, you do your keep, change, flip. 18 over 60 times 60 over 42. This is why it's really nice if you don't simplify your fractions till the end, because they can usually just cancel. Okay, so now we get 18 out of 42, which simplifies to 3 out of 7, dividing by 6. Perfect. So instead of doing a Venn diagram, let's do this with a tree diagram. So we've got a conditional probability, right? We have to rain or not rain, and then whether she's late or not late. Okay, so we start by determining whether or not it's going to rain or not rain. So this is the probability that it rains, and this is the probability that it doesn't rain, so not rain. It rains 30% of the time, so this would be 0.3, and this one would be 0.7. So rain, not rain. Then from there, I'm either going to be late or not late. Late or not late. Okay, so this is the probability that I'm late and it doesn't rain. This is rain and late. Rain and not late. Not rain, not late. Okay, so it says Lauren is late to work 10% of the time. So her late probability on its own is 0.1. And her not late would then be 0.9. So, fun little fact, when I go down the branches, okay, so when I follow this path and this path, we get the probability of it raining and being late is just the probability of rain times the probability, did my parenthesis wrong, times the probability of being late. So 0.3 times 0.1, which gets us 0.03. That's for the first line. The second line, probability that it rains and that I'm not late. So the probability that it rains and I'm not late is just 0.3 times 0.9. So that's going to get me 0.27. Okay, keep on going. Probability that it doesn't rain and I'm late. Probability it doesn't rain and I'm late. Okay, I had a rough morning. All right, should have been in good conditions, but it just didn't work out for me. Okay, that's 0.7 times 0.1, so that's 0.021. Okay, so that's good. That doesn't happen that often. Then the last one, probability that it doesn't rain and I'm not late. Probability that it doesn't rain and I'm not late. Okay, so that's what I want to happen, right? I don't want rain and I don't want to be late. I want everything to be all right. All right, let's see how often that happens. We multiply that, we get 0.679, which is actually pretty good because that's about 67.9%. Okay. So we wanted to find, what were we looking for here? Okay. See what color haven't I looked? I haven't done red. Okay. Find the probability that it is raining given that she's on time to work. So, probability that it's raining given I'm not late for work. So, we're going to do the probability of both of those happening. Yeah, this might be easier if I write it out. So, rain and not late over the probability of not late. Well, the probability of rain and not late is 0.27. The probability of not late is 0.9. When you divide that, wait, hold on. Something's not matching up with quantity. Oh, silly me. I was doing the overall not late. That's not what it asked for there. What it's saying here is in my probability instances, when is it I'm not late? I'm not late here, so this probability, and I'm not late here, so this probability. So we want to do 0.27 plus 0.679. So this would be 0.27 divided by 0.949, giving us a probability of 0.285. Okay, so this is another way of doing it as opposed to a Venn diagram. Okay, hopefully this part makes sense when it's not late. Okay, so this is that conditional probability. So when you want to use that tree diagram. Okay, so you really need to know the difference between independent events and mutually exclusive. Independent events means one outcome will not affect the other. So rolling a dice and spinning a spinner. All right, one outcome is not going to affect the other. However, if I were to draw one card out of a deck, not put it back, but then take another card, those are dependent events. All right, one is affecting the outcome of the other. Right? Depends on which card I took, and that changes my probabilities of the next card being selected. Okay, so independent means their outcomes can't affect each other. So they have a special probability, a special formula. So when you do A and B and they're independent, you just have to multiply the probabilities. Now, when they're mutually exclusive, that means that they can't happen at the same time. Okay, like rolling an even and rolling a 5. That can't happen at the same time. They're mutually exclusive. Okay? So there's no overlap is what I'm getting at. Okay? There's no overlap between mutually exclusive events. Example 4 wants us to play a game where we throw a dice and flip a coin. So let's start by rolling a dice. We either want a 6 or don't get a 6, right? Those are our two options. So I'm going to draw my tree diagram. That's the first thing I want to do. So rolling a 6 and not a 6. So this would be 1/6, and this would be 5 out of 6. Okay. Then we roll, we flip a coin. And that's either going to be heads or tails. Heads, tails. And the odds of getting a head is a tail, or it's 1/2. Odds of getting a tail is 1/2 all the way down. Okay, just in general. Now, to get the end result, so getting a 6 with heads. So let's see. So getting a 6 and a heads, the chance is 1/6 times 1/2, so that's 1/12. the odds of getting a 6 and a tail is 1/12. The odds of getting a not 6, okay, these are commas, by the way. All right, not 6, and heads, not 6, and tails. So not heads, let's see, that's 5/12 and 5/12. So, first question, what is the probability that the player will win $20? Well, they win $20 if the probability of getting a 6 and heads. 6 and heads is 1/12. There's your answer. What's the probability that the player will win $1? Well, that's the probability of not getting a 6 and getting heads. Okay, understand the rules of the game, right? Not a 6, but heads up, win $1. So not 6 and heads is 5/12. And the last one, what is the probability that the player will not win anything? So winning nothing is just the probability of not getting 20 or $1, right? So that's just the probability of, well, 1 minus the ones before. So 1 minus 1/12 minus 5/12, which is 6/12, which is 1/2. So you have a 50% chance that you're not going to win anything. Okay? If you have any questions, please ask me in class. All right? I know this is weird. So if I'm not making sense, just ask me. Now for the section questions from 4.62. Now, exam tip. These formulas are in your booklet. Okay? If you haven't already, go ahead and print out that booklet for yourself to have already. Okay? Get familiar with using it. Yes, you can use it on the test. You need to get familiar with it. It is that's the one I always give you on test day. Okay? Now, the first example, Marat is playing a game throwing 2 biased coins. The probability of the first coin, probability of the second coin. Okay, so they're 2 different coins. Find the probability that both coins lands on heads. So, probability of rolling a head and rolling another head, okay, from the 2 different coins. Well, one thing you need to notice is that these are 2 different coins. Keep saying that, hoping that you realize that means they are independent. And if they are independent, then I can use this formula. So that's the probability of rolling a head for the first die. And then I can just multiply it by the probability of the second dice. So that is just 1/3 times 3/4, which is just 3/12, which is 1/4, right? Simplify. Okay? Let's do another one where we don't draw a picture, but we just try to use the formulas. So here, familiar yourself with this. If you draw a picture, that helps too. Okay? So, well, I just told you not to draw a picture. Anyway, so, let's see. I know that I want to find the probability that he chose the blue box given he picked a mint flavored candy. So what's the probability that he picked both blue and mint divided by the probability that they picked a mint? Okay, so let's start with the probability of picking a blue box and a mint. Well, a box and whether or not it has mint candies or not is really, I mean, they're independent of each other. So I can just multiply those probabilities together. The probability of the blue times the probability of the mint. So my numerator is just going to be 1/3 times 19/29. Okay? Now, to find the denominator, we need to think about there's two ways to get a mint, by selecting the blue box or the yellow box. So if we select a blue box, that would be 1/3, and getting a mint candy would be 19 out of 29. But also we can get mint by picking a yellow box, so 2/3, times the probability of getting a mint one there, which is 17 out of 38. Okay, we can simplify this. You can use your calculator. All right, so that becomes, oh goodness, let's see, 19 over 87 plus 17 over 57. Okay, so, oh goodness, so gross. This top number is 19 over 87 divided by the bottom one, which is 854 over 1653. And then this will simplify to, here, let me see. Cognitive is not giving me the exact answer, but I can do that on my calculator. Let me show you. So we can type in our fraction. So let's do second, nope, it's not second, it's alpha y equals number 1. So your fraction is 19 over 87, and then we're dividing that by another fraction. Oh, dang it, I meant to hit alpha. Alpha y equals, oh, I double clicked it. Okay, alpha y equals, enter, then my other fraction is 854 divided by 1653, and we get 361 over 854. Now to make sure that's right, we can go here to math and select number 2 and have it convert to a decimal, and it's 4.423, which is what Cognity had. So 361 over 854. So you can use your calculator to simplify for you, okay, in case you forget those with fractions. Use that. All right, let's do another example. So here we know this relationship is true between these probabilities, okay? So we want to find probability of A and get an answer as a decimal. Well, this one seems to be the most complicated, so let's just take on this one. We can replace the given formulas with probability of A and B divided by the probability of B times another given formula, so another probability of B and A divided by the probability of A here is going to equal 2/9. Well, what's nice here is that we can plug in our values. A and B is 0.2. Probability of B is 2 times the probability of A. And the probability of B and A is the same as A and B, right? 2 and 3 is the same as 3 and 2. So that's just 0.2 here. And the probability of A, we don't know, equals 2/9. All right, so now we've got just the probability of A. Maybe it might be easier if you write it as 0.2 over 2x times 0.2 over x equals 2/9. Okay, so we'll keep on going. So we'll have 0.2, well, 0.2 times 0.2 is just 0.04 over 2x squared equals 2/9. All right, we can cross multiply. We get 4x squared equals 0.36. Divide by 0.4, or divide by 4, we get 0.09, and we get x equals, technically it's plus or minus 0.03, but my probability can't be negative, okay? So it's going to be 0.03 is my probability. Oh, not 0.03, oh, 0.09, the square root of 0.09 is 0.3. And since it can't be negative, right, this is probability, it has to be positive, we only care about the positive one. All right? So I know I did a whole lot of examples, but I try to do everything when it comes to probability because it's the most commonly missed questions on any exam. IB, AP Stat, I'm telling you, probability is the most commonly missed stuff. So make sure you know it. Ask questions along the way. I promise you are not alone. Majority of these questions get missed. So please, please, please ask. Okay? All right? You're not stupid. Okay? All right. I love you, and I will see you in class.